This is Professor Derek Seitz. This video shows how to do hypothesis testing for independence using Microsoft Excel. The idea here is to test two statistical variables to see if they're independent. This is set up with two contingency tables that are associated that have corresponding cells. The first contingency table at the top here is where you enter some data into the blue cells. Those are observed values. One of the random variables will have its attributes in the rows and the other one in the columns. The blue area is large enough to handle a 5 by 5 scenario. That's big enough for anything you'll see in classroom settings. This particular example here is 3 by 3, 3 rows, 3 columns. It's not essential or that important for this calculation to label the rows or the columns of what they actually mean. It's the data itself and the calculations that drive the test. The second table below is the expected values, where for each entry here, such as this one, which corresponds to the 30 observed value above it, the calculation, as you see here, it takes for the 30 the row total times the column total and divides that product by the overall total, which in this case is 300. Every one of the cells down here is set up to do that. Since it's only a 3 by 3 contingency table and the blue area allows for 5 by 5, the non-used or inactive cells must be blank. They will appear as zeros in the expected values using the formula. The null hypothesis for this test is that the two variables are independent. That's how the expected values are set up based on that assumption. The alternate hypothesis is that the variables are dependent. There's a necessary check in order for this test to be valid. For each of the active cells, the expected value must be greater than or equal to 5. So down here in the expected value table, you see there's 9 cells that are active, ignoring the blank 0 cells, and each of them has an expected value greater than or equal to 5. This blue cell, you enter your level of significance for your test, 5% here. It's formatted with 5 decimal places of precision in order to make comparison to the p-value easy to do. Notice that the p-value, the probability value in the right tail of the chi-square test that's used for this kind of hypothesis testing, there's a comment in blue to remind you that you must go into the formula for this p-value and change the ranges to be the active cells. Here you'll see there's chi-square test, and there's 2 ranges. The first range is for the observed values, and the second range is for the corresponding expected values. First range, A2 to C4, that's this upper left entry here. If you were to select it, you would drag from here, so the selection all the way down to the right corner. It would select the 3 rows and the 3 columns, and that's how you get A2 through C4. And similarly, for the expected values, it's A10, which is the 24 value, down through C12, the 20 value down here. Once you set the formula correctly, Microsoft Excel will go through everything for the test and give you the p-value. That means behind the scenes, the test statistic has been calculated, and the p-value result is what you get in this cell. Looking at the p-value and comparing it to alpha, we see that it's smaller. P-value smaller than your level of significance. That means there is enough evidence to reject the null hypothesis. The p-value is small enough, the probability is small enough to reject the null hypothesis that the variables are independent, and therefore at this level of significance at 5%, we will make the decision that they're dependent. There's another tab in this spreadsheet that's important because for students in classes doing problems will often ask for the test statistic value itself, which Microsoft Excel doesn't reveal. This tab over here, clicking this, has all the information, all the calculations needed to calculate the test statistic. All you need to do is make sure in these 2 blue cells right here, the number of rows and number of columns, that's the active rows and active columns in the contingency table on the first sheet over here, which we know is 3 by 3. Don't forget to enter those, and then the degrees of freedom is automatically calculated by the formula rows minus 1 times columns minus 1. The observed values and the expected values are automatically replicated here for you. Notice that the blank cells appear as 0 here. They do not affect the result negatively. When you add in zeros, it makes no difference to the answer. Observed values, expected values, and then these columns go through the step-by-step process to calculate the test statistic. First, observed minus expected in this column, corresponding to each row, the observed minus its expected. And then next column, the square of the previous column. And then the last column, each entry is the squared value divided by the expected value. And the test statistic is the sum of all the values in this last column. You can see that here. It's the sum E6 through E30. And the p-value is not copied from the previous tab. Instead, it's calculated using the chi-square distribution right tail, passing in the test statistic and the degrees of freedom. And notice that the p-value over here is 0.00983. That's exactly what we got in the first tab from Microsoft Excel. When those two are equal, that's a strong indicator that everything was done correctly. And you have the same result over here, but you have the additional test statistic to answer those kinds of questions.